Hi, I'm Nick DeMarinis. I'm a PhD student at Brown University, and I'm going to talk about our work Sysfilter, a framework to perform system call filtering for commodity software. This is a joint work with my co-authors Kent, D, Rodrigo, and Vasilis, and all of us are from Brown University. As software evolves, we've seen an inevitable trend that programs will grow in size and complexity. To give one example, let's look at the common Unix program true, a small utility for shell scripts. Here's a valid representation for that program. It does nothing successfully, and it just returns 0. In version 5 of Unix, the source for this program had 0 lines of code, such you don't even need the return statement. But over time, more components were added, like a version option and a help option to explain the version. And now, on a relatively modern distribution and as part of GNU core utils, this program has over 2,000 lines of code, showing that software is always growing, even for this simple program with literally no functionality. This is a common trend we see across many different kinds of libraries and applications. Having software with more code and more functionality also demands more and more operating system features to support it. The System Call API defines the way programs can interact with the OS kernel. Syscalls provide functions like reading, writing, and opening files, forking new processes, managing network sockets, and more. Every syscall function gets assigned a unique number that denotes the API function being requested. In Linux, the size and scope of this API has grown continually as new features are added. In a study that examined the kernel source from 2005 to 2014, 76 syscalls were added, but only 6 were removed. In the latest stable kernel version, which is 5.8, the API has a total of 350 syscalls for x86-64. So there's a lot of functionality here. The size of this API is very concerning from a security perspective. By default, any program has access to the entire Syscall API, regardless of how many syscalls the program actually requires. This is a blatant violation of the principle of least privilege. An attacker who's able to take control of a program can make use of OS features the program wouldn't normally need by making additional syscalls. So for example, cat or grep don't need to use the network or fork new processes, but if an attacker can achieve arbitrary code execution with them using something like code injection or code reuse, they can make these syscalls and, for example, open a socket. Later in this talk, I'll discuss a study we performed to find the syscall usage of about 30,000 binaries in Debian and SID. Only about half of these programs use the execve syscall to run new programs, and only 34% use the listen syscall to listen for new connections. The remaining binaries have access to this functionality, even though they don't need it. Beyond this, allowing programs access to the entire Syscall API also increases the attack surface of the kernel. An attacker that can make arbitrary syscalls can potentially exploit kernel vulnerabilities in less used and therefore less stressed system calls, allowing them to further escalate their privileges. For example, the ptrace system call was the subject of a privilege escalation vulnerability discovered just last year for kernels 5.1.17 and lower. But only 0.5% of the binaries in our study actually required this syscall, and thus actually needed access to this part of the API. The rest of these binaries are overprivileged in this way. To help mitigate these issues, we present Sysfilter, a framework to automatically find and limit the system calls used by an application. This limits what services an attacker can abuse and reduces the kernel attack surface by limiting the set of syscalls available to each application. In this way, we can better enforce the principle of least privilege with respect to the system call API. In the next few slides, I'll provide an overview of how Sysfilter works and how we're able to effectively improve program security while limiting their Syscall API access. So let's start by talking about the design. Sysfilter has two components, system call set extraction and system call set enforcement. The extraction step occurs offline. We envision it as a component of the application's build or install process. To extract an application's syscall set, we take as input the program in binary form, as well as any shared library dependencies. From this, we use static analysis to construct a safe, tight over-approximation of the program's function call graph to find all its reachable code. From there, we perform further analyses to identify all syscall sites in the call graph and find the set of syscalls actually required by the application. This set of syscalls is patched into the program as a filter, which enforces the syscall set at runtime. In our current implementation, the enforcement uses the seccomp Bpf framework, which runs the filter on each system call to check if it can be executed. This effectively sandboxes the program to using only the developer-intended set of syscalls. In the Syscall extraction phase, we disassemble the target binary and all its shared libraries to build the call graph and find the set of syscalls. We built our extraction tool atop the Egalito framework, which is a binary analysis framework that we helped develop. Egalito is a binary recompiler. It disassembles binaries and lifts them into an intermediate representation that's useful for building further analysis like this. In general, precise disassembly of x86 binaries is an undecidable problem. However, complete and accurate disassembly is crucial for our analysis, since failing to find a syscall site may cause an application to crash. Our tool, and Egalito, is able to perform precise disassembly on all binaries provided that they meet a few conditions. First, all binaries must not interleave code and data. This is true for all code compiled on modern versions of GCC and LLVM. Next, all code must be position independent in order for it to have relocation information, which we use for the disassembly. And finally, binaries must also have stack unwinding information. The last two are true in relatively modern systems. Stack unwinding info is typically included by default to allow inclusion of code in C++ programs, and position-independent code is now common on all modern Linux distributions to support ASLR. Finally, if debug symbols are available for binaries or shared libraries, Sysfilter can use them to improve the precision of our call graph. I'll explain more about how we use debug symbols to improve our precision in a moment. To build the call graph, we recursively follow the program's control flow to find all reachable functions. To illustrate this process, on the right is an example program composed of 7 functions. The entry point, main, calls f1, which returns a pointer to f3. f3 is stored as a function pointer, which is then invoked. The remaining functions are present in the program, but not used. Our goal here is to construct the set of all functions that can actually be invoked by the program, which is all the code reachable from the entry points. So to start, we begin at main and add it to our call graph. Next, we recursively add any direct call instructions contained in these functions. So here we find and add f1, and then continue searching any functions called from f1. In this case, f1 makes no additional calls, so our call graph at this point just contains main and f1. Next, we consider any indirect call instructions present in the program. Indirect calls are those made through a register or memory address, such as calls from a function pointer. In this case, we have one indirect call in main, which is fp. Determining the complete set of targets of an indirect call is a hard problem due to the imprecision of points to analysis, which doesn't provide complete results in the general case. Instead, we need to over-approximate the set of targets by considering all functions that are address taken in the program to be the targets of indirect calls. Address taken functions are those that have their address used on the right-hand side of an expression. Since all our binaries are position independent, we know the location of all address taken functions based on the relocation information provided in the binary. Here we have 4 address taken functions, f3, f4, f6, and f7. These functions are the complete set of potential targets for fp, so we need to add each of these to our call graph. Next, we visit each function that was added and recursively consider any direct and indirect calls that they make. So here, f3 is empty, but f4 has a direct call to f5, so we need to add it as well. Our call graph is now a significant over-approximation of the true call graph, but it's guaranteed to be complete. Next, we'll discuss ways that we can prune the FCG to eliminate some of the function calls that we know are unused. To start pruning, we can recursively remove functions that only have their address taken in code that we know is not part of the call graph. So here, f2 is never actually called in the program, and this is the only place where f4's address is taken, so we can remove f4 from the set. As a result, we can remove f5 as well, since it's only called from f4. If debug symbol information is available, we can take this one step further. Using the symbol locations, we can find objects like arrays of code pointers or other statically initialized data structures. If these structures contain address-taken functions that are otherwise unreachable, we can prune them in the same way. So in this case, f6 and f7 in the pointer array are never referenced, so they can be removed as well. We call this pruned representation the vacuum call graph, or VCG. The vacuum call graph is a tighter but still complete over-approximation of the program's function call graph. This is only a high-level view for how we build the VCG. For more details on how functions can be pruned, please refer to our paper. Once we've constructed the function call graph, we visit each reachable function to find all the system call sites and their syscall numbers. The x86-64 ABI specifies that all system calls are performed using the syscall instruction, with the syscall number loaded in the RAX register. Since syscall numbers are fixed values, we expect that most syscall sites follow a pattern like the example here, which is just to load a constant value into RAX shortly before executing the syscall instruction. At each syscall site we find, we do a simple value tracking analysis with usedef chaining to find the register value. While it's not guaranteed that we can always resolve the syscall number statically in this way, we found that it was nearly always successful. One exception is glibc's syscall function, which makes arbitrary syscalls based on its arguments. In this case, the syscall number is just the first argument to the function call, so to handle this we apply the same value tracking approach just to get the first argument register. Overall, we found this approach works really well for all the binaries we examined. There's a handful of isolated exceptions, which we discuss more in the paper. Once we've assembled the set of syscalls for a program, we enforce the binary by generating a filter program that restricts its execution to the syscall set. Our enforcement uses seccomp Bpf, a facility built into the kernel for making policy decisions about syscalls. Seccomp Bpf is widely used in production today with handcrafted policies for applications like OpenSSH, Google Chrome, and container runtimes like Docker. On each system call, seccomp executes a Bpf program that determines whether or not to allow the syscall. To do the enforcement, we generate a Bpf program that checks if the system call is contained in the syscall set that we found in the extraction phase. Let's consider a program that has the following syscall set, which is just 5 syscalls. We tested 2 methods for structuring the Bpf program to look at its performance impact. Our first method is a simple linear search that checks the call being made against each one in the set. We can improve this using what we call a skip list filter, which is essentially just a binary search to reduce the number of checks we have to do. Once we generate the Bpf program in either format, it's patched into the binary as an extra shared library dependency with a constructor that calls the filter before main is executed. This installs the filter at program start and effectively sandboxes execution to the syscall set. Next, I'll discuss our evaluation. We evaluated Sysfilter across 3 dimensions: correctness, performance, and effectiveness in terms of security gains. To ensure that Sysfilter does not break programs when enforcing a syscall policy, we used Sysfilter to enforce programs from 11 applications with extensive unit test suites. After enforcing each binary in the application, which was about 400 binaries total, we ran the unit tests from each project to ensure that all the tests still pass. In total, we ran over 38,000 unit tests across all the projects. In each test suite, we excluded tests where the enforced binaries would need to execute other programs. These tests are challenging for the enforcement due to the way filters must be inherited when invoking new processes. We talk about several methods for how these cases can be handled depending on the application and the security requirements. For more details on this, please take a look at our paper. To look at Sysfilter's performance, we ran some HTTP request benchmarks on an Nginx web server that we enforced with Sysfilter. Here, we compare the relative throughput of the server using our 2 different filtering methods, linear and binary search, at different request sizes. We also examine the performance difference with and without the kernel's just-in-time Bpf compiler. When the Bpf programs are interpreted on each syscall, so when JIT is turned off, as we would expect, we see that the skip list filter has better performance compared to the linear search method. For the smallest request sizes, we see a drop in throughput of 18% for the linear search, compared with only 7% for the skip list filter. When we enable JIT, it seems to mitigate the difference between the filtering strategies. We see only a small reduction in throughput, max of 6% in the worst case, for both filter types. This shows that we can enforce the web server system call usage with minimal impact. We also conducted similar performance tests for the Redis data store server and the Spec 2006 benchmarks. For more details about these experiments, please see our paper. We conclude our evaluation with a large-scale study of system call usage. We extracted the system call sets from over 30,000 C and C++ binaries in Debian and SID. To do this, we gathered a list of all packages across the distribution's 3 main repositories, main, contrib, and non-free, and we exhaustively downloaded, installed, and ran our extraction tool on each package and its dependent shared libraries to try and get as close to complete coverage of the whole repo as possible. We chose SID, the unstable version of Debian, for its high availability of debug symbol packages. Obtaining complete coverage on this branch is a hard problem because packages are continuously being updated and subject to breakage. In total, though, we successfully examined over 30,000 binaries from over 8,900 C and C++ packages. Across the whole repo, the median time to extract the syscall set was about 30 seconds per binary, with 90% of binaries completing within 200 seconds. In the next few slides, we summarize some of the insights from our large-scale study. More details are, of course, in our paper. Here, we plot a CDF of the number of syscalls observed across all binaries. We found that all binaries, even the minimal form of bin true from the beginning of the talk, can use at least 40 syscalls. This is due to all the functions that can be required by the dynamic loader, even before main is invoked. The maximum number of syscalls used by any single binary is only 215, which is only 62% of the total set of 347 syscalls. The median was only 90 syscalls. This demonstrates that overall, binaries are overprivileged in terms of the Syscall API. To show the effectiveness of our call graph pruning, we can compare the size of the syscall sets at each stage of the call graph construction process. Remember that we can compose the vacuum call graph in 3 steps. First, we follow all the direct function calls, then we over-approximate all the possible indirect call sites, and then we prune address taken functions that we know can be safely removed to obtain the VCG. So in the plot here, the green points represent the number of syscalls for each of the 30,000 binaries when building the call graph from just the direct calls. As we'd expect, if we add in all of the indirect calls, which are the blue points here, we find significantly more syscalls for all binaries. Accordingly, the number of syscalls for the vacuum call graph, the orange line, falls somewhere in the middle. For every binary, the number of syscalls found for the VCG is always in between the other 2 versions. For some binaries, the difference is pretty significant. For some, we're able to prune more than 50 syscalls compared to the version with all the indirect calls. Overall, this shows that our vacuum call graph approach improves our analysis by providing a safe but tighter approximation of the function call graph. Finally, we can look at Sysfilter's effectiveness by measuring its ability to reduce the kernel's attack surface. We compiled a list of recent CVEs in the kernel related to particular system calls. A subset of the more recent ones are shown here, more in our paper. For each CVE, the column on the right shows the number of binaries in our study that would still be able to attack the kernel using those syscalls if the programs were enforced with Sysfilter. Many of the CVEs involve namespaces. The checkmark next to the syscall list means that namespaces are involved in triggering that vulnerability in some way. The more common syscalls listed here, like clone, unshare, and socket, are only needed by 60% of the binaries in our study. The remainder, which is about 10,000 binaries, will never make these syscalls during normal usage. So enforcing them with Sysfilter would prevent an attacker from using one to invoke these syscalls and attack the kernel. The benefits are even more significant for the less common syscalls like ptrace and pivotroot, which are only needed by a very small set of binaries in the whole distribution. This shows that Sysfilter can mitigate real-life threats by enforcing least privilege access for some of these less common syscalls that are otherwise not needed by many applications. So to wrap up, we've presented Sysfilter, a framework to find and restrict Syscall API usage using static binary analysis, which can improve application and kernel security by enforcing the principle of least privilege. Our implementation is open source and available at the link here. If you have any questions, please feel free to reach out to me via email. Thank you.